Let's start this course series with a question related to its title. What is digital logic? Digital logic is the foundation of digital systems. It refers to the use of Boolean algebra to represent and process information. At the basis of a logic circuit are logic gates, such as AND, OR, NOT, and derived gates. Logic gates implement basic logical operations and process signals taking only two discrete values, 0 and 1. A logic circuit is therefore composed of a set of interconnected logic gates, properly selected and combined to implement the desired functionality. Logic circuits are divided into combinational and sequential circuits. A combinational circuit is a logic circuit whose output depends at any given time only on the current values of the inputs. An example is the multiplexer shown here. At each instant, it outputs either the value of input data A or input data B, depending on the value of the control signal C. As we can see, a combinational circuit forms an acyclic graph of logic gates that generates a flow of bits from the inputs to the outputs. Unlike combinational circuits, a sequential circuit is a logic circuit whose output depends not only on the current values of the inputs, but also on their past history. For example, the circuit shown in the slide analyzes the input values in the current and previous clock cycles to check whether the value 1 has occurred at least once and sets the output accordingly. As we can observe, a sequential circuit includes memory elements, such as flip-flops, to keep track of the history of input values. The circuit can no longer be represented as an acyclic graph. Instead, it may form feedback loops involving the memory elements. Returning to the title of the series, let us pose another question. How are logic circuits designed and implemented? The process of implementing a logic circuit is called logic synthesis. More precisely, logic synthesis is the procedure that takes as input a behavioral specification of the system to be implemented and produces as output the logic circuit that realizes such behavior. The first aspect to address is the system specification. It is necessary to rigorously and formally define the behavior of the system to be implemented starting from the design requirements. This behavioral specification will be the input to the synthesis process. The second aspect is the synthesis process aimed at generating the circuit. As we will see, the number of logic circuits that can implement a given specification is, from a theoretical point of view, infinite. The goal of logic synthesis is not only to translate the specification into a circuit, but also to identify the most convenient implementation according to a set of non-functional design requirements, such as maximizing performance or minimizing the size of the system to be implemented on the chip. For this reason, the synthesis process also performs an optimization of the circuit based on one or more metrics used to estimate the characteristics of the system with respect to the non-functional requirements under consideration. This course series will mainly focus on optimizing the size of the logic circuit in terms of the number of logic gates required for its implementation. In some cases, we will also analyze system performance, that is, the time required for a circuit to produce an output in response to each input stimulus. A final fundamental aspect of synthesis is the need to automate the process using a computer. The systems to be implemented generally have complex specifications, and the resulting circuits can be very large. Managing the synthesis process, including the search for the optimal solution, cannot be handled manually by the designer. For this reason, significant effort has been devoted over the years to defining algorithmic and systematic methods that can be implemented in software and executed automatically by a computer. Therefore, this course series will study logic synthesis not only from a design perspective, that is how the designer defines the system specification, but also from an algorithmic perspective, presenting basic approaches to automated synthesis. To better understand what we are going to study, I would like to place the topics of this course series within the overall digital system design flow. We therefore extend the discussion from the previous slide by adding further details and additional aspects. As we have already seen, the first step is design at the behavioral level. At this stage, we analyze the functional requirements, that is, the informal description of what the system is expected to do, and we define a specification that describes its behavior. For this reason, it is called a behavioral or functional specification. In this phase, possible non-functional requirements are also analyzed, such as constraints on performance, area, or power consumption that the final device must satisfy. The behavioral description is usually translated into a register transfer level description, commonly abbreviated as RTL. At this level of abstraction, the system is specified through an architectural or structural model that interconnects functional components, such as adders, multiplexers, and registers, typically taken from a library. In addition to these basic library components, project-specific components can also be defined. For example, the control unit that coordinates the activities of the entire system is usually tailored to the current design. The goal of the RTL description, which was not mentioned in the previous slide, is to simplify the management of large designs. Indeed, it decomposes the overall behavioral specification into smaller subfunctions, each implemented by one or more interconnected components. The interaction among all these components eventually realizes the overall functionality of the system. The next step is logic synthesis, which is the main topic of this course series. Logic synthesis takes as input the register transfer description of the system, or in some cases, a behavioral description, and generates the corresponding logic circuit. After the logic level design, further processing steps are carried out at the physical level. Examples include floor planning, placement, and routing. These steps transform the input logic circuit into the final physical implementation, mask data for ASIC fabrication, or configuration data for programmable devices. In this course series, we will mainly focus on the upper part of the flow, stopping at the definition of the logic circuit that implements a given specification. This is the part of the flow most closely related to the topics typically covered in computer engineering. The following physical design phases, which depend on the chosen technology, are more closely related to electronic engineering and semiconductor implementation. At the other end of the flow, we will also briefly discuss register transfer design and the basic functional components used at that level. You should already be familiar with processor schematics from your previous studies in computer architecture, which is therefore an important prerequisite for the topics covered in this course series. That said, this first course focuses on combinational logic, discussing approaches for defining specifications and basic synthesis methods. In the first videos, we will introduce Boolean algebra, that branch of mathematics that allows us to formally and rigorously describe logic circuits. We will study how, based on the properties of Boolean algebra, a specification described by a logical expression can be transformed into another one that is mathematically different but functionally equivalent. This process forms the basis of optimized synthesis, whose goal is to identify the logic expression with minimum cost. We will examine various optimization algorithms, starting from exact methods, which are typically used to obtain two-level circuits, that is, circuits with a first level composed only of AND gates and a second level composed only of OR gates. We will see that due to the computational complexity of the synthesis process, these methods can only be applied to small circuits. For this reason, the design of complex circuits generally relaxes the two-level constraint and relies on multi-level circuits. Moreover, instead of exact methods, heuristic approaches are preferred. That is, algorithms capable of identifying good solutions, although not always optimal ones, within a reasonable design time. In the second part of the course, we will address the design challenges of a specific class of combinational circuits, namely arithmetic circuits. We will explore number representation, which should already be partly familiar to you, by reviewing the binary representation of integers, both signed and unsigned. We will then study the representation of real numbers, with particular attention to floating point representation. For each representation format, we will examine how to perform the basic arithmetic operations: addition, subtraction, multiplication, and division. We will then study the architectures of the arithmetic modules that implement these operations. Due to the specific characteristics of arithmetic operations and the circuits that perform them, the design of arithmetic units must be approached from a different perspective. Rather than relying only on the synthesis methods studied previously, we will see that these modules are designed by identifying architectural patterns directly derived from the arithmetic algorithms they implement. In particular, we will see that regularity, modularity, and scalability are essential features of arithmetic circuits. These properties together with the need to support operands of arbitrary bit width, have led over the years to the development of specialized and optimized architectures that provide high performance and reduced area. Such architectures are commonly reused in digital system design without requiring their synthesis to be performed from scratch each time. This concludes this introduction. Welcome again and enjoy your study of digital logic.